So today we will talk about the approximate solutions for ordinary differential equations. Okay. Approximate solution for first order ODE. Sometimes not all the ODE, first order ODEs you can solve analytically. So we will use the power of the approximate solutions or numerical solutions to help us to get the first order ODE solution. Okay, sometimes a simple iterative technique is useful for trying to get a general idea of solution for first order ODE. Okay. And today we will start talk about the approximate solution such as Picard iteration. Okay. Picard iteration. And for this Picard iteration, what we are trying to achieve is trying to get many iterations so that our solutions is closer to the true general solution of the first order ODE. So the scheme of the Picard iteration is construct a sequence of function to get closer to the general solution of first order ODE. And let's make an general form of Picard iteration. So let's make an example, a general form for the first order ODE f y prime equals f x y. And we are solving this for an initial value problem. So we are giving an initial value of x0 equals y0. And how we can use the Picard iterations for this first order ODEs. This ODE actually, this has a formal solution, which you know that at step n, which is x, will be equals to the initial value plus whatever the integral of this function. So it's from x0 to x, f x, y, x, dx. So that is the general form of this first order ODEs and how we use the Picard iteration. The first is giving an initial value for this x. And we can guess, or from the problem, we already know what is the initial x. So the zero step will be y0x. So using this sub-zero to represent this is the zero step, and y0x is usually the initial value of that first order ODE. So which is usually y0, which is equals to yx0, right? So that is the initial value. Then the next step is calculate the first step, compute y1x, and this y1x using this formal solution form will be equals to y0 plus from x0 to x and f x y x. Instead of yx, we know what is the y0x, so will be the y0x here. And dx. So that will be the first step of the Picard iteration. We know y0x. In order to compute the y1x, we use the y0x in the integral part. And then you will similarly can get what is the second step, which is compute y2x will be equals to, okay, y0 plus from x0 to x, fx, instead of the zero step y0x, we already compute the y1x, which will be more accurate to get closer to the general solution of the first order PDE, which will be here, y1x dx. Then we can compute n step. So the solution will be closer to our final solution of the first order ODE for n step. So we compute ynx. That will be equals to y0 plus x0 to x, f x y n minus 1, which is the first step, dx. So this is the Picard iteration. Of course, as you go larger in numbers, it will have many steps, and the general solution, I mean the Picard solutions at n step will be closer to the general solution of the first order ODEs. And we will make an example of how to use Picard iteration, but this is the general form, okay? Let's make an examples. For example, let's choose first order ODEs and trying to use both the exact solution as well as the Picard iteration to solve the general form of this first order ODE. Okay, let's do it. The example will be y prime minus y equals 2x with an initial value problem, which is y0, give you the initial value is y0 equals to 1. And you know that this is first order linear ODEs. So you can have the numerical solutions for these equations. And for the Picard iteration, first, the zero step is giving an initial value, right? So the zero step is guess, what is our y0? Y0x will be usually equals to the initial value, will be 1. So when this x equals to 0, okay? And then the next step, the first step for Picard iteration is trying to get what is y1x. So we compute y1x will be equals to y0x plus, you know, it's integral, right? The integral, which is from 0 to x. And we know that this y prime is equals to 2x plus y, right? So we know the integral part will be 2x plus y0x dx. And you already know this y0x is 1. So we can get y0x plus from 0 to x, 2x plus 1 dx. y0x is 1 plus, this integral is pretty simple, so you can integral by yourself, which is x squared plus x. So that is the form when you compute the Picard iteration, the first step. Then we can use this first step solutions to compute our second step. So the second step, compute y2x will be equals to y0x plus from 0 to x, right? and the 2x plus y1 x dx. Okay, and you know that what is our y0x, which is 1, and from 0 to x integral 2x plus y1x, you know y1x is from the first step 1 plus x squared plus x. So we put 1 plus x squared plus x dx. And that is from 0 to x, 3x plus 1 plus x squared dx. And this integral is also very simple. It's a polynomial integral. So that is final solution for the second step will be 1 plus x plus 1 over 3x cubed plus 3 over 2x squared. Okay. Then, you know, as you go n step, the solutions from the Picard iteration will be getting closer and closer to the general form. But we will stop here. It just to give you a general idea how this Picard iteration will work. Then we will try to solve it numerically, trying to see whether our solutions is indeed suitable for this first order linear ODEs. Okay, so for the exact solutions, we can get the analytical solution for this first order linear differential equation, which we get analytical solution for y prime minus y equals 2x with the initial value problem y0 equals to 1. And you know this is first order linear ODEs. So what we get, the first step for this one is trying to get the integral factor gx, so that this first order ODE will be exact equation. Then we can integral to get our u, right? So the gx, the integral factor gx, and we already derived that earlier in the class, which is e to the px dx. And you know the px, right, is minus 1 here. So the px is minus 1, e to the integral minus 1 dx. That is e to the minus x. So it's very simple for this gx. Well, after you have this integral factor, this e minus x y prime minus e to the minus xy equals e to the minus x 2x. This is an exact equation. And we also know since the d e to the minus x y over dx will be equals to e to the minus x ey over dx plus y times d e to the minus x dx. And that is equals to e to the minus x y prime minus e to the minus x y. And you see these equations on the right hand side is exact equals to the left hand side of this first order linear ODEs, right? So that is equals to e to the minus x 2x. Then we are trying to get, you know, what is our exact solution. So we can see that just the integral both sides, then we can get our final solutions, right? So e to the minus xy, just the integral both sides here and here, that will be equals to e to the minus x 2x dx. And you learned that integral before that if you have integral u dv, that will be equals to uv minus v du, integral v du. Then let's just trying to figure out what this integral look like in the end. So we have our u. Let's assume that u is equals to 2x. v will be equals to e to the minus x dx, right? That is separate from here. U equals 2x, v equals to e to the minus x dx. Sorry, this should be dv. dv will be equals to e to the minus x dx. So this is u dv, and that's u dv. Okay, then you can get what is our v. So this will get du will be equals to 2 dx. Okay, and then this will get uv will be equals to minus e to the power of minus x. Then we can get this integral, which is e to the minus x 2x dx will be equals to uv, which is 2x times minus e to the minus x minus the integral of the v part minus e to the minus x du, which is times 2 dx. Okay, and then you can just integral this part and to get the final solution, which is minus 2x e to the minus x minus 2e to the minus x plus some constant. And in order to solve this constant, we need our initial values. So this integral is equals to e to the minus x, right? Then we get e to the minus xy will be equals to minus 2x e to the minus x minus 2e to the minus x plus some constant. Then we can just times e to the x to cancel out all this exponential part. So y will be equals minus 2x minus 2 plus c e to the x.